Chapter 8, Section 4. This is the next section after 8.3. 8.3 covered geometrical treatment of vectors. We're going to go over an algebraic treatment of vectors and then go a little bit into it with specifics on scalar multiplication, vector addition, and then we're going to talk about a type of vector multiplication. We're going to restrict ourselves to just 2 dimensions. We're used to working in 2 dimensions anyway. The x and y coordinate grid is a 2-dimensional coordinate system. So when it comes to 2-dimensional vectors, there is a way to multiply 2 vectors together, but it ends up becoming a scalar in the end when we multiply them. So the product ends up as a scalar. We normally call it a scalar product. This book's calling it the dot product, which is a very, very common name for it. So let's see. 8.4, and how do we define vectors on the coordinate plane? Which there's a bunch of stuff on here, and I'm going to go ahead and move this over to the side. So I'm going to draw my own coordinate grid. So let's say we have our own coordinate grid. So we have points x, comma, y on our coordinate grid r with a 2 on it. So or r squared. So this is going to be the representation of the coordinate grid. So we have an x-axis and a y-axis. And then we can denote a member of this 2-dimensional space as an ordered pair, x, comma, y, where x is the number along the horizontal axis, and y happens to be the number along the vertical axis. So how do we incorporate the idea of a vector? So we want to turn this into what we call a vector space. So we call this a vector, or we can call this a vector if we think in terms of the origin first as the initial, and then draw an arrow pointing towards that point, which you can call that point P. And because the initial point is the origin, we can call that point O. So then we have the vector, we can call that vector U, which geometrically is OP. So from O to P in this particular way. And that's going to be the way that we can define these two. So what we end up doing is we can also come up with a coordinate way to describe these. And I'm not sure how far along this goes. Yeah, it gives an A and a B. So the way that we do this to describe vectors, this is first off 0, 0. We can call that x, comma, y. And in this case, since I called them x, comma, y, which over there they called it AB, then we're gonna have what we call a right triangle. So we're gonna think of these things with a directional angle because it's the coordinate plane, and we've already discussed how to draw angles in the coordinate plane using standard position. We're going to be incorporating angles into this too. So there'll be an angle, what we call theta. There's going to be a right triangle here. Now we're going to be calculating lengths of vectors using the Pythagorean theorem pretty much, or distance formula is another way to find side lengths. So, and that comes from the Pythagorean theorem, which we've seen before. So the way that we define vectors then is we take the coordinates of O, so the coordinates of O were 0, 0, the coordinates of P were x and y, and we're going to not draw this as an ordered pair. It's going to look like another type of ordered pair, which it still is an ordered pair, but these don't represent points. These will represent movement between points from one initial point to a terminal point. So instead of using what's it called, parentheses, we're going to use a triangle bracket. So it's kind of a new one, a triangular bracket. So you take the coordinates for P first. So it's going to be the x coordinate for P, which in this case it's x. And you're going to subtract 0 from it because that's the x coordinate for O, the origin, comma, and then you have y minus 0 because that's the y coordinates and the difference between the two in the order of P and O. So it's P minus O. So in this case, we take U to look like this, x, comma, y. And really what that is how far apart horizontally we moved. So that's from here to here. This is x. And then the second number is how far vertically we're moving. So it's not a coordinate, it's a what's it called? They're instructions on how to move. You move x horizontally and you move y vertically. So it moves, or you can think of this as a force, because forces are vectors. It's a force that moves something on a point O to something, or to point P. So the movement is from O to P. And we think of that movement in two directions or two dimensions. So how far in the x direction, how far in the y direction. We call these actually components. So x is the horizontal component. That's the x component. Not a coordinate now, it's a component. And this is a y component. And that's if we started at the origin. We could start anywhere we want, which I'm going to go ahead and give another set of 2 points on the coordinate plane. So let's say I have a vector, let's say u and v, or not a vector u and v. Let's say we have another point, let's say P, over here. P has coordinates, let's say xp and yp, just to say that that's the x coordinate for P and the y coordinate for P. And let's say that that point moves over here to, let's call that Q. And Q has coordinates xq, yq. So then we want the vector u, which goes from P to Q. And how do we denote this vector in the coordinate plane? So first off, we can draw it with an arrow between these two, from P then to Q. And then what we do is we draw a right triangle based off of this. And the right triangle is going to be drawn in such a way that one of its legs is parallel to the x-axis and the other leg is parallel to the y-axis. So that way we can talk about a difference between coordinates. So then the question I'm going to ask then, what is the coordinate representation of that vector? Well, like we did earlier here, we subtracted x and y coordinates. Here it's the same thing basically. So we have the first point, the terminal, or the initial point, sorry, with coordinates xp, yp, and it moved to that point q with coordinates xq, yq. So we want to think of separately what the movement was horizontally and the movement was vertically, so separate from each other. So to find out where this moved to, or how far it moved to and in what direction, we subtract the terminal and the initial in a specific order. Terminal minus initial, like we normally do in a physics course. Final minus initial. So the final x coordinate was xq. Its initial was xp. For the y coordinates, because that's in the x position, so in the y position, this is going to be yq is where it ended up, minus where it started, yp. And that's how we form a vector given 2 points in the coordinate plane. So you need a specific order, and the terminal point where it ended up would be the number you start with, and then subtract the number in the initial point. So there's our definition for how to actually create a vector given 2 points ordered. So it starts at this point P, ends up at this point Q, and that's how we determine what the two components are for that vector, the x component and the y component. So here what they're doing is they're talking about how to form the magnitude of a vector. So I might want to continue this discussion a little further. So let's say we stick with P and Q. So whatever those two are, these have a x component distance. We'll call that A. And also a y component. We call this y, or not y, b. I'm using their letters. They had an A and a B in there. So we could think of these as right triangles. And the right triangles are going to be drawn in such a way that one of the legs is parallel to the x, the other leg is parallel to the y-axis. So then these are two legs on a right triangle, horizontal and vertical. A is the horizontal component, B is the vertical component. So when we talk about the magnitude, this is the vector u, by the way. The magnitude of the vector u, there's a way that we show this symbolically. So the vector, the whole vector quantity, is a letter with an arrow on top. If you take away the arrow, then we're talking about the magnitude. Or you can keep the arrow. A lot of times mathematicians will draw absolute value symbols, because absolute value symbol is used for distance. So this is the symbol that I think this textbook uses for the magnitude of a vector. In physics, they're a little lazier because they draw a lot of these things out. They just get rid of the arrow on top. So if there's a letter with no arrow on it, it's a scalar quantity, and it represents the magnitude of that vector. So it's the magnitude of u, and there's a formula for it. Magnitude of u, just like we saw in the previous handout, is going to be the hypotenuse, the length of the hypotenuse of that right triangle that we drew there. So the magnitude of u, according to the Pythagorean theorem, if I square that quantity, it's equal to a squared plus b squared, because a squared plus b squared is equal to c squared, and we can think of c as the magnitude of that vector, which is the hypotenuse of the right triangle. So you square root both sides. We assume those are positive quantities, which they're going to be positive quantities. You square a positive quantity, you get a positive quantity in return. I don't need to do a plus or a minus. It's going to be the positive square root of that. So this is the formula for the magnitude of a vector. Very, very important. If you know the x and the y components of a vector, you square those two components, add them, square root it, and that's going to be the magnitude of the vector. So that's where this formula comes from. Oh, and here they're given an extra little bit of information. So we were talking about the angle earlier. So it says the magnitude or the length of a vector u, which is given by two components, a and b, is given by the following: the square root of a squared plus b squared. And then they're also defining what the angle theta. So on the coordinate plane, we're going to use standard position. So in standard position, the angle is measured from the horizontal, positive horizontal that is, going counterclockwise. So we'll call that theta. So how do I find out what theta is? To find out theta, you think of this again as a right triangle, and because it's a right triangle, I could use trig. So I can use any one of the trigonometric ratios I'd like: sine, cosine, tangent, cotangent, cosecant, secant. We're going to use tangent. Since we're talking about x and y components anyway, we want to use the x and y components, and x and y happen to be the opposite and the adjacent. In this case, b and a are the opposite and the adjacent, respectively. So I'm going to use tangent. So tangent of theta is the opposite, which is b, divided by a, which is the adjacent. So that's how we define the angle theta for a particular vector. So that's going to tell us the direction also. So vectors in two space or in the coordinate grid have a magnitude, and we have a formula for the magnitude, no problem. And they also have a direction, and the direction is going to be given by this equation here: tangent of theta is equal to b over a. And the direction is going to be represented by the angle theta. Example number 1. Find the magnitude and the direction angle for u, which is given by -5, 4. Now you remember, those are going to be components of the vector. So if you wanted to think of this very simply, so the simplest way that we can represent this vector, you can draw it stemming out of the origin. You can draw it stemming out of any point you want, so why not pick the origin? So say from the origin, which has coordinates 0, 0, and then those are not coordinates. These are movements from where you're at currently to where you got to end up, the terminal place. So it ends up looking like those are coordinates because we're starting at 0, 0. So it's because that we started at 0, 0 that those look like coordinates. So what we're going to do is you're going to move horizontally -5 and then move vertically +4. So let's say -5 is out over here, +4 is up over here. We're going to end up at this point in the second quadrant. That's if we start at the origin. We could have started anywhere else, and then I'd still have to move 5 to the left, up 1. So that's what that means. So the vector u is equal to -5, 4. That's what that really represents. From where you're at, move 5 to the left, and up 4. That's what vectors are. Move this way, and that way, if that makes sense. So here I'm drawing the vector u. And what do they want? They want the magnitude, and they want the direction. So we got to be really, really careful. The magnitude will be the length of that vector. In this case, it's going to be the hypotenuse of the right triangle that we just formed, this right triangle. And this right triangle has side lengths 5 this way and 4 this way. So we'll start off with magnitude of u, which is, we denote that by drawing absolute values on the outside. And the formula is square root of, you could just look at the components. It's negative 5, you square it, plus 4, and you square it. So I could have just not drawn it at all, and I could have gone towards the, or I could have looked at the, what they gave me. U is equal to negative 5 comma 4. Could have just plugged straight in. So that's going to equal to square root 25 plus 16. 25 plus 16, 41 I believe. Square root 41, that is. And that's going to stay that way. Square root of 41, 41 does not reduce. It's not a multiple of a square number, so there's nothing that can reduce outside of that square root. It stays that way. Now what about the direction angle, theta? Now if we're going to talk about multiple vectors, you can also say that that's the angle for u. So I could put in subscript the notation for u to say that that's the angle direction for u. So there's a formula. Tangent of theta is equal to b divided by a. So then theta should equal to inverse tangent of b divided by a. Or it's going to be related to that. Right? So if you remember, inverse tangent's only going to give you an angle on the right half of the circle. That's going all the way back to 5? 7.5? So inverse tangent will only give you angles from negative pi over 2 to pi over 2. So if you use your calculator here, it's not really going to help much. Or it'll help, but it's not going to give us the final answer in one shot. So we'll still have to do some work. So I'm going to go ahead and go to my calculator. So we're talking about inverse tangent of b divided by a. So inverse tangent of b in this case is 4. A is negative 5. So remember, it's the vertical component divided by the horizontal component. Tangent is always y divided by x by definition. So we're taking the inverse tangent. I'm doing that on a calculator. Inverse tangent of negative 4/5. And I'm getting negative 38.7 degrees. I'm going to round to the nearest tenth of a degree. So negative 38.7 degrees. So what is it giving me? And if I draw that in standard position, it's giving me this angle. Negative 38.7 degrees. Now remember, we were to expect an angle between negative pi over 2 and pi over 2, or negative 90 degrees and 90 degrees. That's all the calculator is good for. So between negative 90, positive 90. So that does not tell me directly what the angle is that I want. Remember, angles are supposed to be in standard position, and in this case, the angle that I want in standard position is from here to here. I want that angle. It's a second quadrant value, so it's going to be somewhere between 90 degrees and 180 degrees. Question is, how do I find it? The nice thing is I have this negative 38.7, which gives me this measurement of that angle here. So it's actually telling me what the size of this angle is, but negative. So in that one, so the one that I have drawn in the second quadrant, it's positive. So this one here should be 38.7 degrees. Because of a symmetry, those are vertical angles. Okay, so if that's the case, if that one's 38.7, the angle that I want, which is the other way around, starting from the positive x, theta, is going to end up equaling to, well, the way that I would probably do this is take 180 degrees total and subtract the one that was given, 38.7 degrees. So if I take 180 degrees and subtract 38.7, you're going to get 141.3, I believe. Yeah, 141.3. I don't know why I verified that in the calculator. I knew it was right. So that's theta. This is the angle that we want. And remember, angles have to be written in standard position, starting from the positive x-axis, ending up at the terminal. In this case, the vector is the terminal. So that one is example number 1, finding the angle between, or the angle of a vector to show its direction, and finding the magnitude. And that's done completely using the coordinates, x and y coordinates, or in this case, those are called components. And components are understood using a coordinate grid. That's number 1. Okay, how to find the horizontal and vertical components of a vector. So here are the formulas, but I'd like to give a explanation of where those formulas come from. So we'll go ahead and derive them. So again, we start off with some vector v. And I could draw that vector v however I'd like. We'll draw it here, and I'll probably just draw it in the first quadrant. So let's call this vector, or u, not v. So that's our vector u. So our vector u could be broken up into two orthogonal components or perpendicular components. B, A. A is vertical, or sorry, A is horizontal, B is vertical. So then I could rewrite u with two components, A and B. Okay, so I'd like to come up with a formula for those two components. So let's say I know the magnitude, and let's say I know the angle. So then how do I come up with the components? So this is a trig problem. We should know that sine of theta is the opposite over the hypotenuse. In this case, b over magnitude. We should also know that cosine of the angle theta is equal to the adjacent, in this case a, divided by the hypotenuse, in this case magnitude of u. So those two are true for any vector. So I could have drawn that in the second, third, or fourth quadrant, and that still would have been true. So if I wanted to solve for the quantities a and b, I could take these two equations, multiply both sides by the magnitude. So you would get magnitude of u times sine theta is equal to b. That's the vertical component. This one you would get magnitude of u times cosine of theta is equal to a, and that's the horizontal component. And the only reason I have the vertical first and the horizontal second is because I thought of sine first and cosine second. You should usually think of cosine first. But it doesn't really matter which way you think of it, as long as you have it in the right order, right position. So those are the formulas for the vertical and horizontal components respectively. Here they wrote the horizontal first, then the vertical. So the formula for A is the magnitude of u times the cosine of the angle. The vertical component is equal to the magnitude of the vector times the sine of the angle. And you could rewrite it this way instead. Think of it in terms of magnitude and direction angle instead. So going back to the geometrical understanding, it's just a distance and a direction. So there you have distance and direction showing up in the formula or for the representation of that vector in two dimensions. And what that's going to do also is it's going to beg the question of can we just think of vectors as those exactly, distances and directions? That actually gives rise to other types of coordinate systems. So the coordinate system we grow up with is the rectangular one, horizontal and vertical. Or if we add a third dimension, it's horizontal, vertical, and then outwards. So some other perpendicular direction. So like you have paper is a plane, and you have a left and a right and an up and a down. Then the third dimension is outside of the paper. So here we could think of, here we can change that rectangular system to what we call a polar system, which has just a distance and an angle. And that's one of the sections that we're going to be going over in this particular chapter. I think that's 8.7. So more on that later. So let's see, number 2. So vector v in the figure has a magnitude 14.5 and a direction angle 22 degrees. Find the horizontal and the vertical component. So backwards, they gave you the direction and the angle. Find the x and y values, or the horizontal and vertical values. So we just use those formulas that are up here, and I have them up here. So if I want the horizontal, so I can call it horizontal. Then the formula would be the magnitude of the vector u times the cosine of the angle theta. And they gave those to us. 14.5 times cosine of the angle, in this case, is 220. 220 degrees is not a special angle. So that's not one that I know off the top of my head. That's probably one I want to use a calculator for. Now, if it were 210, then maybe. Or 240, then maybe. But if 220, that's not one of the values that we had memorized on our unit circle. So 14.5 times the cosine, 220, I'm still in degrees, and we're getting And this is perfectly normal, negative 11.1076. And why is that normal? Why should have I expected a negative value? Well, first off, we're in the third quadrant, so quadrant 3. The x component is supposed to be negative for something in quadrant 3. So there's absolutely nothing wrong with that value. So we're also expecting a negative vertical component, no? Since in the third quadrant both x and y are negative. So the vertical component, magnitude times sine. Same 14.5. In this case, this is sine, but of the same 220. So the only difference is sine versus cosine. So horizontal is cosine, vertical sine. And that's an easy way to remember because cosine was x anyway, sine was y when we thought of the unit circle. So it turns out to be kind of natural. So 14.5 times sine, 220 degrees. And I'm getting negative 9.3204. And I could box both of those, and that's all they want. So those are the horizontal and the vertical components, which you can rewrite this vector u. They didn't ask, but I'm doing it anyway. Negative 11.11, comma, negative 9.32 if I round it to the nearest hundredth of a unit. So they just wanted these. But that's how you would do it if you were given a direction and a magnitude. Example 3. Write each vector in the form a comma b, which I just did that, so that's one of these. So they gave you the magnitude and the direction. So the final answer is going to be something like this in the end. So they want this and they want this. You plug it into that formula. I'm going to go ahead and skip that. So these aren't something I'm going to spend more time on. This I'm going to spend more time on. These are vector operations. Two of them are going to be what we have to predefine. So these have to make sense geometrically. And some other mathematician already defined this for us, so they have it there. So here's the definition of vector addition. So that first one, that's the definition of vector addition. That's how you add two vectors on the coordinate plane. And it works. It's going to work the same way geometrically. So if you wanted to do a proof that that's the same vector addition as the one that we saw in 8.3, it works out so that way that forms the resultant on a parallelogram. So the diagonal of a parallelogram, it works out the same exact way. This one is scalar multiplication. And it works the same way in the geometrical system that we saw in the previous section. So that's how we define, so that's also a definition. Those are the two operations that we define in order to make the coordinate plane what we call a vector space in higher level mathematics. So, as a result, if we define vector addition and scalar multiplication this way, this is what we call the equilibriant, the negative of the vector. Equilibriant. So that's the physics term basically. Also, vector addition, if you take the addition of the two vectors, the result of those is called the resultant. Also that physics term that we saw in 8.3. And then this is just a demonstration of how we subtract. So to subtract two vectors, you would add the negative of the second vector to the first vector. So we really just need to understand the first two, vector addition, scalar multiplication. So to find the negative of a vector, you multiply that vector by -1. And to multiply into a vector, so whatever number we're multiplying into a vector, that's going to get distributed into both components. So when we multiply a vector by a number, you multiply both components by the same number. That's how you scale a vector. How do you add a vector? You add corresponding components, A and C together, B and D together. So it's the horizontals together, and then you add the verticals together. That's how you add two vectors. So we're going to demonstrate that in number 4. Whoops. So not too many of them, A, B, and C. So for number 4, we're going to let u equal to 6, -3, and v equal to -14, 8. So they just wanted an example, and those look like random numbers. Find each of the following. So letter A, u plus v. So what I'll start off with is rewriting what the definitions for u and v are. 6, -3, and -14, 8. Same order that it shows. So u first, then v second. Okay, so then we go by the definition of addition. According to the definition of addition, the final x component is the sum of the two individual x components. So you take both x components and you add them. So in this case, 6 plus negative 14. 14 was negative, so you just move the negative in there with it. And then negative 3 plus 8, because 3 was already negative. So we're not subtracting, it's just because those components were negative to begin with. Then we just simplify. 6 minus 14, negative 8. Negative 3 plus 8, positive 5, I believe. And that's it. This is u plus v. Notice how they're not drawing arrows on their vectors? They have it in bold. And that's normally in a textbook, a mathematics or a physics textbook. They don't draw arrows on top, they just write it in boldface. So we draw arrows because we can't really recreate the boldface. In our writing at least. You can try, but I'm not gonna. So letter B, negative 1/2 times v. So we're taking v and we're scaling it by this factor negative 1/2. So that one's the second one. We got to go by the definition of scalar multiplication. You're multiplying a vector, by some scalar quantity. So a velar, if you want to talk about it that way. This is negative 1/2. And then we need the components for v, which is negative 14, 8. And it's basically distribution. So it's like a distributive property, pretty much. You distribute the negative 1/2. That's going to be negative 1/2 times negative 14. And we'll simplify that in the next step. Negative 1/2 times 8. Negative times a negative is a positive. 1/2 of 14 is 7. Negative 1/2 of 8 is negative 4, I believe. And this is negative 1/2 v. Did I box this one? No. And then we'll look at letter C. This is what we call a linear combination. Mathematicians always want to sound pretentious, basically. And they want to, like every little thing that's new, they'll give a name for it. So if what you're doing is you're combining scalar multiplication and vector addition together, it's called a linear combination. And there's actually a reason for it. There's an important distinction to be made in higher order mathematics, especially when talking about transformations from one vector to another vector. But in this course, if I use those terms, it's because I want to sound smart. That's all it is. So it doesn't really help us out. That's called a linear combination of two vectors. So what we're doing is we're combining them some way linearly by addition and scalar multiplication. So we rewrite the definitions for u and v. So 6, negative 3, and then plus 2, negative 14, 8. And then we scale each individual one. So we're distributing the 5 into the first and then the 2 into the second. So hopefully I do this right. That's 30, negative 15. I'm going to double check it because I make mistakes. And then we have plus. You can leave the plus on the outside and you're going to have negative 28, 16 it looks like. And let me double check that. And it looks fine. This equals. Now I got to combine these two. There's addition on the outside, so I just write 30. And in this case, it's going to end up being minus 28. It's going to be plus a negative 28, but I can skip that step, hopefully safely. Negative 15, and then plus 16. And we think of these individually. We get positive 2 and positive 1, it looks like. Hopefully you got the same thing. And this is the result of combining 5u and 2v. So if you just follow the definitions for vector addition and scalar multiplication, I didn't use these at all. It's really just the first two. So the first two should have been there, and the other two maybe not. But they're important to point out anyway. So that's example 4. We're not going to go over too much more. No, not at all. No. There's still quite a bit left in this section. So what I'm probably going to go ahead and do is I'm going to stop this here and then pick this up where I left off in the next video. So this will be part A. The next one will be part B for this is 8.4.